Hello. Yeah, Ramcharan. Hi, how are you? Good, good. Okay, so what we have discussed last class, Ramcharan? Bioma. Okay. Okay, meter rotation, no? Can you see the screen now? Okay, so who are not there? Aditya. Kondanya? Okay. Let him come. I'll give you some questions on organic, okay? Yeah, hi. Simple question. What is the name of this compound? IUPAC name. Tell me the name. What about others? One chloro first. When you write down the name, it should be alphabetically 1, 2, and 3. Right? So 3 bromo, 1 chloro, cyclohexane. First we'll write bromo, then chloro. Okay? Right. What is the name of this compound? Now, 2 or 3? Why 3? Why not 2? That's what I'm asking. 2 or 3? Amog? Amog? 3. Okay, 3 chloro is correct. Why? You see, whenever we have double bond in the ring, okay, see, we have to follow rules. We cannot go with our own emotion, right? So rules we have to follow in nomenclature. So whenever we have double bond in the ring, we always give first and second position to the double bonded carbon atom. That is the rule, right? So this carbon atom will get 1 or 2, or this carbon atom will get 1 or 2. So numbering will be what? We are bound to give first and second position to the double bonded carbon atom. That we cannot change. Now the two options are there. We can write this as 1, 2, and like this 4, 5, 6. Or we can write this as 1, 2, 3, 4, 5, 6. So in this, we'll follow this pattern. This numbering, because you are getting here at third position. From this side, you are getting here at sixth position. So this is the numbering we have. It should be 3-chloro-cyclohexane. Understood? So that's the rule. Like whenever we have double bond in the ring, we always give first and second position to the double bonded carbon atom. Okay. One question you see. Um, this is crown ether. Okay, and we write it as X crown Y. All these question has been asked. Okay, X crown Y. You have to tell me what is the value of X and what is the value of Y. Yes. Any idea? Number of oxygens. See, Y is the number of oxygen. Okay. And X is the number of carbon plus oxygen. Okay. So X represents the number of carbon plus oxygen atom present, and Y represents the number of oxygen atom only. So X value will be, how many carbon atoms are there? Hmm. 6 oxygen. So Y will be 6 and this will be 18. This one. Name. IUPAC name. Try cyno. What is the name of this one? Dinitrile. Okay. You see, first of all, the name of the first one is 1, 2, 3, 1, 2, 3 tricyano propane. Okay, numbering will be this. In this case, the numbering will be this: 1, 2, 3, 4, and 5. So it will be 1, 5 pentane dinitrile. Okay, the rule says what? Whenever you have carbon containing functional group attached to the unbranched alkane. Okay, carbon containing functional group attached to the more than two, right? More than two carbon containing functional group attached to the unbranched alkane, then we don't consider this into the parent chain. You must have remembered that we always start numbering from the carbon atom of the cyano group. Even for carboxylic acid also, we start numbering from the carbon atom of this functional group, right? So, but in this case, when we have more than two carbon containing functional group attached to the unbranched alkane, then we don't consider this into the parent chain. It will be 1, 2, and 3 tricyano-propane, right? But here we have two carbon containing functional group. So we have to start numbering from this carbon or this carbon. Both you can do. 1, 2, 3, 4, 5. So we have 5 carbons, so pentane dinitrile. Understood this? No, 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 you cannot write. This is not a functional group now. We are not considering this as a functional group. So we cannot write nitrile. It is propane simply. And with propanes, few carbon hydrogen atoms are being replaced by the cyano group. Fine, but when we have more than two functional group present, then we don't consider that into the function this parent chain. Then you can write down triol, triol. The rule is, listen to me. The rule is what? When we have more than two carbon containing functional group attached to the unbranched alkane, that is the rule we have. Okay, so we cannot write down nitrile here. Simply, if you write down this CH3, CH2, CH3, what is this? This is propane. And how this compound differs from this? You replace one hydrogen by CN group here, another hydrogen by CN group here, and another hydrogen by CN group here. So in this propane, one hydrogen has been replaced by this cyano group. That's what we write. So this is the rule basically we are following. One more question we'll see. This one. Others? Correct. First and second position will give here 1, 2, 3, 4. We cannot give 1, 2, 3, 4, 5, 6. Lowest set of locants will follow, right? What is the name of this compound? CHO. This was single bond. CN COOH. What is the name of all these compounds? No. Have you seen this kind of question? Acha, this one. First, you tell me this one. What is the name of this compound? This one. These three, you tell me. Ethyl cyclopropane. Ethyl cyclopropane. This one. Cyclopropyl propane. Okay. And what about this one? Cyclopropyl butane. Okay. First of all, you see this one is correct. See, whenever we have ring and alkene group attached with the ring, so the parent chain will be excuse me, parent chain will be either ring or this parent chain, depending on the number of carbon atom present here. So if the ring contains more number of carbon atom, more or equal number of carbon atom present in the branch or the subsequents, then we always consider ring as the parent chain. You get this? If the number of carbon atom present in the ring is greater or equal to the number of carbon atom present in the subsequents, then ring will be the parent chain. Clear? This is the rule. So parent chain is this ring here, 1, 2, 3. So ethyl cyclopropane, correct? This will be again the parent chain will be ring only. So it is propyl cyclopropane, correct? This is propyl cyclopropane. Here the parent chain will be the substituent because it contains more number of carbon atom. So what we'll write into this? 1 cyclopropyl butane. Right? This is the substituents now. Parent chain is butane. So cyclopropyl butane, 1 cyclopropyl butane. Correct? Now if I give you this one, cyclobutane, and here we have CH2CHO. Ethanol, right? Because when the substituents contains functional group, then this will be the primary chain 1 and 2. This becomes the substituents now. When functional group is there, then we don't see the number of carbon atom. This is the parent chain now, this is substituents. So let 2 cyclobutyl ethanol, correct? Understood all of you? Now the difference in this question and this question is what? That here the functional group attached directly to the ring, right? Even in all these examples. But here it is not directly attached, correct? So now for this kind of question, we have another rules here. And the rule is what? Whenever, write down this if you don't know, write down this. Whenever carbon containing functional group is directly attached to the ring, is directly attached to the ring, then we use following suffix. If the functional group is CHO, then we use carbonaldehyde. Okay. If the functional group is COH, then it is carboxylic acid. Carboxylic acid. If it is nitrile, then it will be carbonitrile. Right. If it is C double bond O, OR, then it is carboxylate. Alkyl carboxylate basically we write. So when this one you have to write down, so this will write cyclobutane carbonaldehyde. Get this? It is cyclobutane carbonaldehyde, cyclobutane carbonitrile, cyclobutane carboxylic acid. Clear? When you have this compound, one more example I'll write down on the same rule. C double bond O, O E T, ethyl, COR, this one. So in this we'll write first ethyl here. We'll write first ethyl, then we have cyclobutane, and last what we'll write? Cyclobutane carboxylate. Understood? Okay, so these are the few specific rules we have, which is important for exam point of view. Others, you know already in basic thing that you can do. Okay, the few specific rules I have revised already. Okay, so we'll start then. Meta rotation we have done last class. Okay, so glucose, everything we have done. No, Haworth structure of glucose and all those structures. Okay, so now the thing that we have already done in the last class, similar discussion we'll do for fructose also. So we can go a bit faster today since we have discussed those concepts in quite detail in the last class. Same kind of thing we have for fructose here. So you write down fructose C6H12O6. Now in this you see the structure of fructose is this: CH2OH, C double bond O, H OH, OH H, OH H, and the last again we have CH2OH. Okay, so if you see the structure of glucose and fructose, you compare, you see this part is common. Excuse me. If you leave the first two carbon atom, the last four carbon atom has the same configuration for glucose and fructose. Yes. Right. So this is one thing. This is important. We'll use this in few minutes later. We'll use this particular concept once. Okay. So you just keep in mind the last four carbon atom has the same configuration as we have in glucose, right? And if it is what? D or L fructose. What structure it is? D or L? How do we configure that? How do we understand that where is D or L? Huh? Yeah, so we have to see the chiral carbon which is at the maximum distance from the primary functional group. Primary functional group is ketone into this. In glucose, it was aldehyde. So 1, 2, 3, 4. At fourth position is this, the chiral carbon, and OH is present on the right hand side. So we call it as D fructose. If you write OH on the left hand side, it is L, right? And this information I am giving you, it is D minus fructose. Like there we have D plus glucose and D minus glucose. Similarly, this structure is D minus fructose. L structure, if you draw when OH on the left hand side, then that will be L plus fructose. Okay. Now in this, the same thing we'll discuss, that is cyclic hemiacetal. Cyclic hemiacetal structure. Cyclic hemiacetal structure. Okay. So now you see in this also, if I write down this structure again, that will be CH2OH, C double bond O, H, OH, OH, H, CH2OH. Okay. Now the same thing, what happens into this lone pair, the carbon atom which is the maximum distance from the primary functional group, the chiral carbon, this lone pair attacks onto this carbonyl carbon, right? And this pi bond goes here. Condania is there? Okay, Condania, you asked me one question, no? That benzoic acid and benzaldehyde, right? See, you cannot. Okay, I'll discuss this. Okay, later, let it be. I'll discuss this. I have discussed this also in the class, but I'll tell you. Okay, let it be. We'll discuss. So this will attack over here. Pi bond goes here. Okay, and again we'll get the structure here like this. This is exactly same that we have discussed in case of glucose. I'm writing down this quickly. Okay, so you just copy it down. OH can be this side. CH2OH can be on the left hand side, and then everything will be same. H here, OH here, OH, H, H, and this is connected with oxygen here, and here we have CH2OH. Okay, plus another possibility is what? That this OH on the left hand side, and that structure will be this CH2OH, OH, H, OH, OH, H, CH2OH, and this is connected with oxygen here, H this side. Okay, so when OH on the right hand side, it is alpha, right? And since this one is what? Alpha, sorry, this one is D minus fructose, just now we have discussed. So this one is alpha D minus fructose, correct? Because OH on the right hand side, and this is beta, sorry, it is beta D minus fructose, OH on the left hand side. Understood? And these two are what? These two are anomers. What are anomers, if you remember? What are anomers? Tell me. Anomeric carbon. And what is anomeric carbon? OH and OR group. OH and ether linkage will be there, right? So this carbon is the anomeric carbon here. This carbon, right? This carbon is the anomeric carbon. And here the configuration is different. That's why these two are anomers. Okay. Here it is, this carbon was planar. The reason I have discussed already in glucose also, this was planar. So this attack can be from the top or bottom. So two different configuration possible. That's why it is alpha and beta, and they are anomers of each other. Okay, finish this. Can I go to the next slide? Yes. Okay. Now for this, you see, we have the another one, that is Haworth structure. Haworth structure of fructose. What is the reference compound we have for Haworth structure of glucose? Furan? No, for glucose I am asking. Pyrene, right? So here the reference structure is, since you see here, I'll go to the previous slide. You see here, the ring that you get here, this ring contains 5-membered ring, right? 1, 2, 3, 4, and 5th is this oxygen. This is a 5-membered ring, right? So we required what? 5-membered compound, right? And that's why the reference compound in case of this is furan. Okay, and the structure of furan is this. This is furan, and this is the reference compound we have for Haworth structure of fructose. Okay, so now when you draw the Haworth structure of fructose, that will be like this. You can draw oxygen, okay, just I'll draw the next one. This is not okay. Now you see this carbon is the second carbon, right? This carbon is the second carbon we have. This one is third, fourth, and fifth carbon, right? Now, if you see the structure, just you refer the structure that I have given you just now, alpha D minus fructose or beta D minus fructose. Okay. The second carbon you see, we have OH on the right hand side for alpha and CH2OH on the left hand side. Okay. Alpha, suppose you have to draw the alpha position here, right? So OH on the right hand side we have, CH2OH on the left hand side on the second carbon. So whatever on the right hand side we'll write down on the bottom, OH here and CH2OH on the top, right? And then we'll go alternate. OH will be alternate. If you see the structure, OH will be here, then OH will be on the bottom, and the last carbon you see, the fifth carbon contains CH2OH and H, right? So OH on the bottom. So here we have CH2OH on the top, and all these position we have hydrogen. Is it correct? Numbering you see, this is the first carbon, second carbon, third, fourth, fifth, and sixth. So whatever group atoms are there on the right hand side, we'll write down on the bottom of this vertical line. And left hand side will be on the top. So this structure represents alpha D minus fructose. For beta D minus, what we'll do? This OH will be on the top and CH2OH on the bottom. Okay, so I'll draw that one also. Here we have OH, CH2OH, and all of the all other things are same, right? OH will be on the top here, OH here on the bottom, and then CH2OH on the top. And all these position we have hydrogen present. Okay, now you see this structure is beta D minus fructose. Okay, and the name of these compounds we call it as fructofuranose. Okay, like there we have glucopyranose, it is fructofuranose, fructofuranose. Okay, both compounds are fructofuranose, alpha 1, and this is the beta. Now, the three-dimensional view, if you try to understand, this is again the thick line we have, this carbon. Means, if you see this molecule, these two carbon is coming towards you, and this oxygen is going away from you into the plane. Understood? Can you imagine this? See, these two, this molecule, this bond is coming towards you. So if you are looking from the front, you see from your whatever laptop that you have, if you're looking this molecule from the towards the screen, it means these two carbon is coming out of the screen towards you, and in the same plane, it's parallel to yourself, right? Like you, when you're watching this, when you're looking at this molecule, this you are at the same plane, parallel plane, and these two carbon is coming towards you in this plane, and this oxygen is going backside of the laptop. Can you imagine this? Three-dimensional structure. So when you see this structure, this OH on the top, right, and CS2OH on the bottom. So if you look at this molecule from the top view, if you see, then what you'll see on the top view? OH, OH, H, CS2OH. Fine? Understood? If you're looking at this molecule from the top, then you will see OH, OH, H, and CS2OH. And from the bottom, if you see, you'll see CS2OH, H, OH, and H. Fine? So this is the structure of beta D minus fructose. What? Okay, fine. Can we move ahead? Now, one thing we can we should also observe here, when we turn this molecule, right? Turn means upside down. We are rotating this molecule. Just flip, right? 180-degree flip. So when you flip this molecule 180-degree, so obviously, oh, just let me write down. This is first carbon. This is second carbon, third, fourth, fifth, and sixth, right? So when you flip it 180-degree, then second carbon will be here. Yes or no? Fifth carbon will be here. Correct? And whatever atoms or group which is there in the bottom, that will come on the top. And the atoms or group which is there on the top will go in the bottom. Fine. Okay. So now when you draw this structure, you see what difference we get here. When you flip it upside down, okay. So first of all, here what should we write? Here, tell me. Okay, let it be. First, tell me which of like this carbon is, what is the number of this carbon according to this molecule? According to this molecule, what is the number of this carbon on the right hand side? This one is fifth, right? This one is fourth. This one is two, right? Now on the fifth carbon, what should be on the top when you flip it? H, because here we have hydrogen. You see on the fifth carbon, you see hydrogen is on the bottom, right? So when you flip it on the fifth carbon, hydrogen on the top and CS2OH on the bottom. Fine. This is CS2OH. And this carbon is what? This carbon is the sixth carbon, right? Fourth carbon, you see, fourth carbon, hydrogen on the top, OH on the bottom. So here we have OH on the top and hydrogen on the bottom. Third carbon, OH on the top. So here we have OH on the bottom and H on the top. Second carbon, OH on the top. So here we have OH on the bottom and CH2OH on the top. Fine. This is 6th carbon and this is 1st carbon. So when they'll give you this structure in the exam, so obviously they will not numbering this carbon atom. They will not do the numbering like this. They will simply give you this structure. Okay. So what is the difference between these two structures? Can you observe? Look at the molecule and you see what is the difference we have. Switched. So the difference is only that here we have in, suppose now you imagine that there is no numbering here, only you have this molecule given. But what happens, we generally see when you draw the Haworth structure of fructose, you will get this structure. Yes, you'll get this structure, and when you flip it, you'll get this structure. The only difference is what, since numbering is not there, so when you give you this structure, you will get confused. Okay, the structure where we have on this carbon, we have OH here on the top, according to this, correct? But since we have hydrogen here, right? We have hydrogen here and OH here. So the point is, you don't have to get confused with this because both structure are nothing but same. In one structure, you are looking from the top, and the other one you are looking from the bottom, right? So whether they give you OH here or H here, the structure is nothing but it is a structure of beta D minus fructose. Is it clear? So once in JE, they have given this structure, right? So don't get confused with this, that here we should have OH, here we should have H, and here we should have OH. If this is the structure also given, the structure is nothing but same, only the view angle is different. Okay, here we are looking from the top, and the same molecule, if you look from the bottom, you will see this. Is it clear now? Okay, so this is one important thing we have. Now another thing you see, which is again important, and that you write down: differentiation of glucose and fructose. Okay, how do we differentiate this glucose and fructose? Now you see glucose. Glucose primary functional group is what? Aldehyde. Now you see the basic properties of aldehyde and ketone, basically we have to compare. Okay, since it has one hydrogen present, this hydrogen, that's why glucose is easily what? Oxidize or oxidizable, right? Even by mild oxidizing agent. We have discussed this already, right? Mild oxidizing agent, since hydrogen is present over here, right? So all these glucose will get oxidized by the reagent called Tollens reagent or filling solution. And you can also recall that when we are doing aldehyde, we have discussed that aldehyde gives Tollens reagent and filling solution test, right? So in this also, this aldehyde, if you see, I just give you a quick recall of this: C double bond O and H. When you put Tollens reagent into this, then it gets oxidized into what? Acid. Aldehyde oxidized into, sorry, it is not double bond OH, right? And this is nothing but the silver mirror test we have, right? Silver mirror test. So test you must go through, it's important. Okay, silver mirror test. Filling solution, if you put this into filling solution FS, you'll get again acid, that is carboxylic acid, and the color that you get here, that is brick red color because of Cu plus. All these things we have already discussed, right? Brick red color due to the formation of Cu plus, right? But if you talk about fructose here, right? So if you remember, ketone does not give this reaction with tolerance reagent and failing solution test, right? Since fructose, the primary functional group is what? Primary functional group is ketone. And since ketone, if you put tolerance reagent or if you put failing solution, both of this, there is no reaction at all because there is no hydrogen present onto this, right? These are weak oxidizing agent. Since hydrogen is not present for ketone, oxidation of ketone requires comparatively stronger oxidizing agent. That's why with tolerance reagent failing solution could not oxidize this, right? So ideally, if you say since fructose contains ketone as a functional group, so it should not give tolerance reagent failing solution test. Yes or no? Ideal situation should be this only, right? But fructose gives this test. This question is very important. They have asked many times in NEET exam also, right? A few questions are in this chapter is important. One of the question is this one. And if you remember, I have discussed this in aldehyde and ketone, that ketone does not give, but fructose having keto group as primary functional group, but then also it gives tolerance reagent and failing solution test. Reason we'll discuss now, right? So first of all, you write down here, it should not give this, but write down into this. Fructose contains ketone group. Fructose contains keto group as primary functional group. Then also it gives. Then also it gives positive test to tolerance reagent and failing solution. Okay, this is one thing. Now the point is why it gives positive test, right? Okay, so the reason you write down next, and the reason you can understand by a rearrangement, and that we call it as, name is not important but I'll write down, that is Lobry D Van Brian Eckstein Kenstein rearrangement. Okay, the name is not at all important, you can skip this also, but I have just given it once. This rearrangement, because of this rearrangement, fructose gives positive test, right? Now what is this arrangement? Okay, so you see, I'll just write down one reaction here. This one is glucose, C double bond O, H. Here we have OH, H, H, OH, OH, H, OH, H, and CH2OH. This is glucose. Okay. Now, in presence of dilute alkali solution, dilute NaOH, we can use, or KOH, NH4OH, right? This reaction is reversible, first of all, right? And it converts into two different form, and that is this. The first one is mannose. And what is the relation of glucose and mannose? Glucose and mannose. Tell me. I've given you the relation of glucose and mannose last class, and I told you also, if you know this relation, you can draw the structure of mannose also. No, they are not anomers. They are epimers, and they call it. They call what? They call C4 epimers. And what are epimers? The configuration will be different at only at one carbon other than anomeric carbon. Right? I have given you this definition last class. You can go through. Now you see, since glucose and mannose are C4 epimers, so configuration will be different at fourth carbon, right? You see at fourth carbon 1, 2, 3, and 4, OH on the right hand side. So in mannose, OH will be on the left hand side. And all other structures, all other configuration will be same. So here we have OH at second carbon, H. Third carbon, H on the right hand side, OH on the left hand side. Fourth carbon configuration will be different. So OH on the right. So here it will be on the left. H will be this side. Fifth carbon will be as it is, OH, H. And sixth carbon is CH2OH. So this is what? This is mannose. Plus, it also exists. This converts into mannose and then fructose also. CH2OH, C double bond O, H, OH, OH, H, OH, H, CH2OH. Right? So this is fructose. So in alkaline solution, these three molecules exist in equilibrium. Right? So glucose, mannose, and fructose are in equilibrium in alkaline solution. Right? So if you take a molecule of fructose, then eventually there will be what? There will be in the mixture, there will be glucose also, and there will be mannose also in alkaline OH minus. So you have taken fructose, but because of this arrangement, fructose may convert, some part of fructose may convert into mannose and may convert into glucose. And these two contains aldehyde group as the primary functional group. That's why the mixture shows positive test. Did you understand this? Okay, so that's the reason we have that. The reason, if they ask, you can write in alkaline medium, fructose, glucose, and mannose are in equilibrium. Means when you take only fructose, it will convert into glucose and mannose also. And since glucose and mannose contains aldehyde as a primary functional group, that's why the mixture shows positive test. Right? Mechanism also you can understand of this reaction. Okay, I will not write down the mechanism, but I'll explain from here only. You see, from glucose, you can draw the tautomers of this. And how do you draw? You see, this double bond comes over here, right? And this hydrogen will leave this carbon and this will attach onto this oxygen. Correct? So you'll get here what? C double bond OH and OH here. Correct? Now suppose this is 1, 2, and 3. And you imagine double bond here and single bond OH here. Fine. Now in this what happens? Again, if this double bond comes over here and this hydrogen attached onto this carbon, then what we get here? Here we get CH2OH and C double bond O. Or chalo, if I write down only this top part here, you see, we have COH double bond C OH, and here it is same, right? This part is same, correct? Here we have one hydrogen already for this carbon. This is the tautomers. Now here 1, 2, 3. If you again draw the tautomers structure of this, you will get what? This pi bond comes over here, and this hydrogen will come out and attach onto this carbon atom. So this carbon already has one hydrogen from here. So CH2OH will get, and here will get what? C double bond O. Fine. So that is how it converts into fructose. Okay, so this is the mechanism of this. Basically, tautomers will draw. Right. Here also you write down this glucose and mannose are C4 epimers. So this is the reason of fructose to show positive filling solution and Tolles reagent test. Yeah. Generally, these tests takes place in alkaline medium only. Okay. Now write down into this. So another thing is what, since I forgot to tell you one thing in the last thing, you can write down here also. Since you see this aldehyde may oxidize by weak oxidizing agent, right? Weak oxidizing agent, and for this ketone, we required strong oxidizing agent comparatively, right? So if you take a strong oxidizing agent, then whether you have aldehyde or ketone, that will get oxidized for sure, right? Understood? See, if aldehyde will get oxidized by weak oxidizing agent. So if you take a strong one, then whether it is aldehyde or ketone, it will get oxidized into acid, right? Then we are not able to differentiate whether the molecule was aldehyde or ketone. Correct. Now, to oxidize this or to differentiate this glucose and fructose, we usually use weak oxidizing agent like bromine water. Okay, so that's the one point to write down. To differentiate glucose and fructose, we require mild oxidizing agent, mild oxidizing agent whose medium is not alkaline. Okay, whose medium is not alkaline. Because what happens when we have alkaline medium? What happens if we have alkaline medium? Into aldehyde, right? And then again oxidation takes place. So the point is, to differentiate aldehyde and ketone, glucose and fructose, we required weak oxidizing agent whose medium is not alkaline. Example, write on bromine water, Br2 with H2O. This is the oxidizing agent we use to differentiate these two compounds, okay, glucose and fructose. Yeah, the same thing. Okay, now we see few reactions of glucose and fructose. Okay, and you also write down the way I'm writing down, because every time otherwise you have to draw the structure of glucose and then the reaction. Okay, so it takes a lot of time. So I'll just write down this. Yeah, write down here first, reaction of glucose, reaction of glucose and fructose. Only one reaction we'll see for fructose. Heading, you write down reaction of glucose and fructose. So in the middle of the page, you write down the structure of glucose first of all. So that will be C double bond O, H, and then we have OH, H, H, OH, OH, H, OH, H, and CH2OH. Okay, this is glucose. Now, when this glucose reacts with, I'll just write down like this, reacts with NaBH4, reducing agent. NaBH4 and then water also we use. Then reduction takes place and this aldehyde reduces into alcohol, correct? So So here we get what? In place of this aldehyde, we'll get alcohol, CH2OH, and all other things will be same. OH, H, H, OH, CH2OH. Okay. Now, if this reaction takes place with a strong oxidizing agent like HNO3, strong oxidizing agent, then what happens? Oxidation takes place and alcohol aldehyde both will get oxidized. Okay, so when this aldehyde oxidizes, it gives acid. All other things are same, and the last carbon here also we have COOH, and here write down as it is whatever the compound it is, right? OH, H, OH, OH, HOH, H and H. What is the name of this compound? It is gluconic acid. Okay, both will get oxidized, aldehyde and alcohol. Okay, now when you do the controlled oxidation of this, like weak oxidizing agent, if you're taking, suppose you're taking weak oxidizing agent, Tollens reagent, okay, or if even bromine water also, Br2H2O. Okay, then this aldehyde gets oxidized, right? And when this aldehyde get oxidized, you will get here COOH on the top, and all other things will be same. OH, H, H, OH, CH2OH. This compound, the name of this compound is glucaric acid. It is gluconic, it is glucaric. Okay. I have given you this structure last class also, I guess. Let me check the name, I think. Just a second. CH2COH. COH, CH2OH, if you have, it is gluconic acid. The first one, this one is gluconic, sorry. This one is gluconic acid, and this one is glucaric acid. We also call it as saccharic acid. Saccharic acid, glucaric acid, both are same thing. This is gluconic acid. Okay. This is a three reaction we have. Now, when this reacts with NH2OH, what happens when aldehyde reacts with NH2OH? H2O goes out and will get oxime, formation of oxime, right? And that will be this. That is here H2O goes out and will get C double bond NOH. This hydrogen will be as it is, and all other compounds structure will be same, CH2OH here. This we call it as oxime formation. This H2 and this O, oxygen, goes out as H2O and NOH joins over here, oxime formation. Okay. Now when this reacts with the last one, this is important. This reacts with phenylhydrazine, and the formula of phenylhydrazine is what? H2N NHPH. One hydrogen is replaced by phenyl, so it is phenylhydrazine. Okay, and we take 3 moles of phenylhydrazine here, And when you take 3 moles of phenylhydrazine, the product that you get here is this C double bond N NHPH hydrogen just a second. Here we have C double bond O, C double bond N, sorry. There's a C double bond N NHPH, NHPH, and then all other things are same HOH, OHH, OHH, and CH2OH. Plus, in this reaction, we'll get PH NH2 out, phenylamine. Ammonia also goes out and water forms. This molecule, we call it as osazone. Okay, it is osazone. This reaction is actually osazone formation. Osazone formation. And this product, we call it as, since it is obtained from glucose, so we call it as glucosazone. Glucosazone. Okay. We can write down the mechanism of this also, but that is not required, so I'm not doing that. Okay. So you see 3 moles of this we are using, 2 moles we use here, 1 mole goes out and NH3 goes out. So this is the 3 moles we are using here. Now the important thing here it is what? You see that I have already told you that the configuration of the last 4 carbon atom in glucose and fructose is same. This one. Right? You see the structure of fructose also, we have this configuration only for the last 4 carbon. Right? So whether you take here glucose or you take here fructose, the compound in osazone formation will be this only. Yes or no? Okay. So if you take fructose, then we call it as fructosazone, glucose and glucosazone. But actually both are same only. Glucosazone and fructosazone both are same only. Why? Because the configuration of the last 4 carbon atom is same in glucose and fructose. Correct? So that note you write down here. Osazone formation in glucose, osazone formation in glucose and fructose is same. In case of fructose, we call it as fructosazone. Fructosazone. Okay, so this is the few reactions we have, which is important. Understood? Okay. Next, we'll see disaccharides. These are monosaccharides. Disaccharides are what? On hydrolysis, which gives two monosaccharides, right? Or which contains 2 unit of monosaccharides, disaccharides. Write down the definition here first. These are the compounds. These are the compounds which on hydrolysis gives 2 monosaccharides. Which on hydrolysis gives 2 monosaccharides. Example, you see, if you do the hydrolysis of sucrose, okay, acidic hydrolysis, it's 3O plus. So you'll get glucose here and fructose. glucose and fructose. If you take lactose, acidic hydrolysis, you will get glucose again and galactose. If you take maltose, again acidic hydrolysis, you'll get glucose and glucose. Right, 2 units of glucose. Now, how to memorize this? You see, if you write down, see, glucose is common in all these, right? If you write down sucrose, then other one will be fructose. If you write down lactose, then other one will be galactose. If you write down maltose, then we have only glucose present. Understood? Like this, you can memorize. One note you write down into this: in disaccharides, in disaccharides, monosaccharides are joined by glycosidic linkage or glycosidic linkage, whatever you say, glycosidic linkage. Okay. Okay. Now, the first thing here you write down, first example we'll see, that is sucrose. Write down the heading. It is formed by the condensation of formed by the condensation of alpha D glucopyranose formed by the condensation of alpha D glucopyranose and beta D fructofuranose. Alpha D glucopyranose and beta D fructofuranose. Right? Now you see how it forms. First of all, we have alpha D glucopyranose. So we can draw the structure of alpha D glucopyranose, right? Alpha D glucopyranose. What should we write here on the bottom? Here you tell me, what should we write here on the bottom? OH. Alpha means OH on the right hand side on the first carbon, and whatever on the right hand side, that should be on the bottom, right? And the second carbon OH again on the right hand side we have. So here we write OH here, then alternate OH here, OH here, and the last carbon we have CH2OH. You must remember, at second carbon OH is always down, right? And whenever you have to write down alpha, then this 2 carbon will be at cis position, means OH will be at the cis position. OH will be down over here, right? So and all other position we have what? Hydrogen present. So this is alpha D glucopyranose. Okay. Now when you write down beta D fructofuranose, so beta D fructofuranose is this. Here we have OH on the top, CH2OH on the bottom, right? So first carbon, second carbon, third carbon OH will have on the top, H on the bottom, OH on the bottom, H on the top, and then on the last carbon we have CH2OH on the top and H on the bottom. Is it clear? Now when condensation takes place, then what happens? This OH and H combines together and H2O molecule goes out, minus H2O. Okay, minus H2O. Now here you see the structure that you get here will be this oxygen, and here we have and these two are connected by the oxygen like this. It should be like this. It is connected by this oxygen, and this hydrogen will be as it is, and here CH2OH will be as it is. And you can draw the other atoms, molecules, whatever it is on this carbon. Everything will be same into this, right? So this linkage that you have, this linkage is glucosidic linkage, right? This bond is glycosidic bond or linkage, whatever you say. Okay. Okay. Now here you see, you write down some properties of this. The first, and which is important, which has been asked in the exam also, it is a non-reducing sugar. Non-reducing sugar. One test you must have written came on test. In that they have asked one of these questions. They have given the structure like this. They have given the structure. Okay, this structure, and they asked whether it is reducing or non-reducing sugar. Okay, so this one is non-reducing. Okay, and then you write down whatever non-reducing sugar we have does not show mutarotation. Does not show mutarotation. Right? I'll tell you just a second. Now you tell me one thing. In this condensation, which all carbons are involved? Like for this one, C1 is involved, right? For glucose, C1 is involved. C1, and for this, what is involved? For fructose, 1 and 2, C2, right? Fine. So this you have to memorize. C1 and C2 are now coming back to this. This C1 carbon you see, it is the actually hemiacetal structure we have, right? OH, OR, and OH. And if the anomeric carbon, possibly this carbon could be the anomeric carbon. This is actually the anomeric carbon we have. You see the structure. Cyclic is this anomeric carbon, right? Here the anomeric carbon is this. Means in fructose, C2 carbon is the anomeric carbon, and in glucose, C1 is the anomeric carbon, right? And sucrose forms by the condensation of glucopyranose and fructopyranose, in which C1 and C2 carbons are involved respectively. Correct? This is the point again you have to memorize. And C1 and C2 carbon is the anomeric carbon in both the compounds. So whenever anomeric carbon is involved in condensation, then the product will always be non-reducing sugar. Right? Point here is what? That if anomeric carbon does not involve in reaction, then reduction takes place at anomeric carbon only. Right? So that reaction is possible whenever anomeric carbon is free, whenever anomeric carbon is not involved in reaction. Okay. So here you see anomeric carbon of both compounds. See, if one of these anomeric carbon is free or does not involve in reaction, then also the product will be reducing sugar. If one anomeric carbon is free, does not involve in reaction, then the product is reducing sugar. Understood? I'll discuss some more example into this. Then you will see how it is reducing and non-reducing. Okay. So out of this three that I've told you, now sucrose, lactose, and maltose, only sucrose is a non-reducing sugar. Understood? And if you see the previous test papers last, I don't remember actually, but second last or previously, like the test you have written from today, if you go through the third or fourth Sunday back, okay, there you have one question, and in that question they have given this structure like this, okay, and they were asking that whether this sugar is reducing or non-reducing. Very simple question. So only thing you have to see what whether this anomeric carbon is involved in condensation or not. If it is involved, non-reducing. If one of these uh, is present or does not involve in condensation, then the product will be reducing sugar. Clear now? Okay. So this is the like the glucosidic linkage we have. So the point you have to like they what kind of question they ask. First of all, they ask whether they are reducing or non-reducing, shows meter rotation or not. Non-reducing never shows meter rotation. Okay, and this glucosidic linkage is present between which carbon? That is also one type of question they ask. So C1 of glucopyranose and C2 of what? Fructofuranose. Okay, so this is what you have to. These three things you have to memorize. Okay, in this you write down. Just a second. Just a second. Somebody. Yeah, okay. So what we were discussing? Uh, okay. Next, write down inversion of cane sugar. Uh, okay. See, actually, I'll just go to the next slide, previous slide. Okay. You see, in this one, glucose and fructose, this is the anomeric carbon, right? And this is the anomeric carbon. Yes or no? Why it is anomeric? Because this is OH and OR attached, right? This is anomeric carbon, correct? So whenever the anomeric carbon is involved in condensation, right, then it is non-reducing. First thing is this. So yes, here you see in this one, this carbon and this carbon is involved in the reaction, right? So that's why the product that you get here is non-reducing. Okay. Now, if any of this molecule, in any of this molecule, if this or this carbon is not involved in reaction, we'll see the other example also, you'll understand. Means if any of this anomeric carbon is free or does not involve in reaction, then the product will be reducing sugar. Because when the reduction takes place, reducing sugar are those sugar which can reduce tolerance and failing solution, right? Reducing sugar are those sugars which can reduce tolerance and failing solution, tolerance reagent and failing solution. So when this molecule or this carbon is free, this anomeric carbon, then only it can reduce the tolerance reagent and failing solution test, or itself get oxidized. If this is not free, then that reaction is not possible. So now just to keep one thing in mind, whenever this anomeric carbon is involved, it is non-reducing. Another example, you will understand why it is reducing. Understood? Okay. So now you write down next, inversion of cane sugar. Inversion of cane sugar. Write down sucrose solution in this only. Sucrose means cane sugar. Cane sugar is nothing but sucrose. Okay. So write down sucrose solution is dextrorotatory in nature. Sucrose solution is dextrorotatory in nature, and on hydrolysis, see, this is something like mutarotation only. Okay, the specific rotation changes on hydrolysis. Okay, the sucrose solution is dextrorotatory in nature, but on hydrolysis it becomes levorotatory, and it converts into D plus glucose and D minus fructose, and it converts into D plus glucose and D minus fructose. The next line, the specific rotation changes from plus 66.5 degree to minus 19.85 degree, right? So you see the change in specific rotation from positive value to negative value, right? So this change in sign, here write down after this, change in sign indicates that inversion takes place. Inversion takes place. Okay, that's the meaning. Next line, write down. Thus, the process of hydrolysis of sucrose. Thus, the process of hydrolysis of sucrose is termed as inversion of sugar is termed as inversion of sugar, and the hydrolysis mixture having equimolar quantities of D plus glucose quantities of D plus glucose and D minus fructose is called invert sugar. This hydrolysis takes place in presence of any mineral acid or enzyme. In presence of any mineral acid or enzyme, which we call as invertase. Invertase, Invertase, right? So the product we get here, that is D plus glucose and D minus fructose, are invert sugar, and the inversion takes place in presence of mineral acid and enzymes. These mineral acid and enzymes are known as invertase. So this is completely theoretical. You have to just memorize this. Okay. Now, next write down, that is maltose. The second one is maltose. Write down to this. It is formed by the condensation of alpha D glucopyranose formed by the condensation of, write down, two molecules of alpha D glucopyranose. Formed by the condensation of two molecules of alpha D glucopyranose, in which C1 and C4 carbon are involved. C1 and C4 carbon are involved. Now you see, and you will understand now why it is invert reducing sugar. So 2 unit of glucopyranose. So draw the structure of glucopyranose here, which will be like this. And alpha D glucopyranose is nothing but this H, OH on the bottom. And then at second position, OH is on the bottom, OH on the top here, OH on the bottom, and CH2OH here on the top. You must memorize this structure because in board you have to draw this structure. Okay, so you must take care of one thing in glucopyranose. At second carbon, OH on the bottom and then alternate. Right? Alpha you have to write down first carbon OH on the bottom, beta first carbon OH on the top. So this is alpha D glucopyranose plus two molecules of alpha D glucopyranose. So again the same structure we have to draw. OH, H, OH on the bottom, H on the top, and then alternate. Fine. Now here you see which all carbon are involved into this. C1 and C4, right? So first carbon is this, and here the first carbon is this, fourth carbon is this. Correct? 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. You see, C1 and C4 are involved. So obviously the glycosidic linkage forms between what? C1 and C4 carbon only. So this position you also have to memorize, because they ask sometimes this question, glycosidic linkage present between which carbon atom? Theoretical question, okay? Options you will have C1, C4, C1, C3, like that. They'll frame the option, okay? So this also you have to keep in mind. Now this H and this OH will condense, right? H2O molecules goes out, and we get the product here, which is nothing but this. OH in the bottom, top, sorry. What is this bond? What is this bond? This is glycosidic linkage. And glycosidic linkage in maltose, it is present between C1 and C4 carbon atom. This is one point you have to memorize. Correct? Now, is this reducing or non-reducing sugar? Reducing. Why it is reducing? Because you see this anomeric carbon does not involve in reaction. So when you put tolerance reagent and failing solution, this carbon will react. Okay, will take part in the reaction. You see in the first example, the anomeric carbon was involved in reaction. Now this anomeric carbon, one of these anomeric carbon is not involved. So the sugar is what? Sugar is reducing sugar. Understood? And when it is reducing sugar, it shows meter rotation. Fine. Okay, so this is what you have to memorize. Now you understood, Ramcharan, how it is reducing sugar? Okay. Now the third one you write down, that is lactose. Third one is lactose. What is the monosaccharides of lactose? Glucose and galactose, right? Glucose is common in all. When you write down lactose, lac means galactose there will be have, right? So write down, it is obtained by the condensation of one molecule of one molecule of beta D galactopyranose, and one molecule of beta D glucopyranose, and one molecule of beta D glucopyranose, in which C1 and C4 carbon atom are involved respectively. C1 and C4 carbon atoms are involved respectively. Understood? Now, with this information, C1 and C4, is this reducing or non-reducing? Hmm. Reducing, right? So reducing sugar. So only now you see the question was so easy. They have given you the structure of glucose also, like whatever molecule it is. They have given the structure, which glycosidic linkage, and then they were asking that whether it is, reducing or non-reducing. Like this, the question was. Exact thing I don't remember, but yes, this was the question. Anyways, so in this you see the two monomer we have, monosaccharides we have is beta D galactopyranose. Can you draw the structure of beta D galactopyranose? Okay, you help me out, okay, because I cannot see whether you can we are drawing or not. So better you help me out. Galactopyranose it is, right? So galactopyranose, we know galactose and glucose are what? What epimers? What position? Uh, Second carbon or fourth carbon? Second, yeah, yeah, correct. Okay, fine. Okay, so I am drawing here beta D galactopyranose. So since it is beta, so OH will be on the top, right? Beta, first carbon, OH on the top. Alpha, first carbon, OH on the bottom. So this is the first carbon. At second carbon, OH on the bottom, right? Okay, OH on the bottom. And third carbon, and just a second, whether it is C2 or I think it is C4 epimers. Glucose and galactose. Yeah, yeah, that's why I said manuals, no? Just a second. Manuals I have given you, C4 I have given you. It's not C4, it's C2 epimers. I made a mistake. I'll just correct it. That's what I was thinking. Glucose and mannose are C2 epimers. Last class you check. Uh, glucose and mannose are C2 epimers, right? And what about glucose and galactose? You cross check once. C4. That's what I'm saying. No. Last class you check what is the relation of glucose and galactose. You tell me that. C4. That's what I am saying. And this mannose are C2 epimers. So what I have given you today, you just check once. No, no, no. Just to correct it, by mistake I have given you that. So glucose and mannose are C4 epimers, C2 epimers, right? So just make correction over there. Here is the thing. It is not C4. It is C2 epimers, right? So just make some correction on this structure also. Here we have OH and here we have H. Here we have H and here we have OH. Right? This correction you make. Okay. So glucose and mannose are C2 epimers. Now, okay. So I'm drawing beta D galactose, right? So OH on the top, beta, second carbon OH on the bottom, third carbon OH on the top, H on the bottom. So ideally this OH should be on the bottom if it is glucose, right? This is the fourth carbon configuration is different. So OH will be on the top, H will be on the bottom, and here it will be same CH2OH on the top and H on the bottom. So it is beta D galactopyranose. Correct? Galactopyranose. Now the another molecule is what? It is alpha D glucopyranose, right? Alpha D glucopyranose. That structure will be like this: oxygen, alpha D glucose, right? So OH on the bottom, H on the top, on the bottom, H on the top, OH on the top, H on the bottom, OH on the bottom, H on the top, and CH2OH here, H here, right? Now, what all carbons are involved into this? C1 and C4. So this is C1 carbon, sorry, it is first and this is fourth carbon. Now the structure that you get here when H2O molecule goes out is this. And here it is attached with oxygen, things like this. So this linkage is what? It is glycosidic linkage. Again, you see this carbon is available here. So at this carbon, reaction may takes place. So this is reducing sugar and shows meter rotation. Then, so this is the thing in all these three examples, you have to keep remember that at what position glycosidic linkage we have, whether it is reducing and non-reducing, right? Now, next one is polysaccharides. Polysaccharides. Right, and these are the polymers of monosaccharides. These are the polymers of monosaccharides. Example, you write down starch, cellulose, etc. Okay. In this, there is nothing to understand. You have to memorize certain points, and this is not important also for exam point of view. Starch, you write down few information about starch you should know. Starch, you write down. It is a white, just in short, you write down. Okay, white amorphous substance. white amorphous substance, present in wheat, rice, potatoes, etc. Starch, when you heat this at 200 to 250 degrees Celsius, you will get another compound called dextrine. Dextrine, N. Write down next. On hydrolysis by enzyme, on hydrolysis by enzyme, one kind of enzyme is amylase, which is present in saliva. Have you heard this amylase? Amylase present in saliva, right? Yes. So this is a kind of enzyme we have. So on hydrolysis by enzyme, it eventually gives glucose, and that's why you see these potatoes and all. When you eat, you'll feel a little bit of sweet taste is there. Okay, that is why, because the starch present in potatoes, when it reacts with amylase, which is present in the saliva, converts into glucose, and that's why we get sweet taste over there. Right? This is one information. Another one you write down: starch solution gives blue color with a drop of what? What? Iodine. This you must have done in titration also. Ionic equilibrium and redox. Right? Iodometric titration. A starch solution gives blue color with a drop of iodine. Okay. Next line, it has two components. First one, write down amylose. First component of starch, amylose. It is a linear polymer. In this, there is no branch. It is only linear polymer. Soluble in H2O. Few properties I'm just giving you. You have to memorize this. But for JEE point of view, it is not important. It is composed of alpha D glucose unit, by glycosidic linkage present between C1 and C4 carbon atom. Glycosidic linkage. That's why you see in C1 and C4, if glycosidic linkage forms, so you'll get a linear polymer like this, and then this, and then this. C1, C4, C1, C4, like this it goes. Understood? That's why it is linear polymer. Fine. So last point you write down, this question they asked in NEET exam. Number of D glucose unit present in this, can be anything between 60 to 300. 60 to 300 glucose unit are present in amylase. Second component of this is amylopectin. Write down highly branched polymer. Properties of this: it is a highly branched polymer. In this also, alpha D glucose units are present, and C1, C4 carbon forms Glycosidic linkage. Insoluble in water, and number of units present, D glucose units present, anything between 300 to 600. Number of D glucose unit. Okay. Okay. Next, write down protein, amino acids, and polypeptides. See, in this one, heading you write down proteins, amino acids, and polypeptides. Write down this. Proteins are made up of polypeptides. Proteins are made up of polypeptides, and polypeptides are made up of amino acids. Okay. So first of all, we'll discuss about amino acids, few structures into this. Then we'll see what is polypeptides, and then we'll see how protein forms. Okay, I'll just give you a brief explanation of protein formation. Okay, it is not that important, but NCERT it is given in so detail. Okay, so there are four different types of structure of this proteins. We have four different stage basically. So all these stages are given: primary structure and secondary, like that, quaternary structure. It's given in NCERT very clearly. So I will discuss those things, but you have to read throughout in NCERT today only, so that you will connect. You will be able to connect those things. Okay, but again, it is not that much important for JE point of view. Only one thing is important in this: some structures of amino acid and then deuterion, that we'll discuss now. Okay, so amino acids are what? These are actually bifunctional organic molecule. Bifunctional means what? What do you understand by bifunctional? Two functional group, right? Bifunctional organic molecule. As the name suggests, amino acids. We have amine also and acid also. Correct? So bifunctional means we have amine present, amino group NH2, and we have acids also. That is COOH. And this is amino. Now, if you see the property of these two groups, this is acidic and this is basic. Correct? So, if you write down some examples here, which is CH3, CH2, 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 COOH. Just write down CH here, and here we have NH2. Okay? So, you see, this is alpha position and this is beta position. So, we call it as what? Beta amino acid. General name. Fine? Alpha and beta, so it is beta amino acid. Generally, the protein that we have is made up of alpha amino acids. Generally, so we'll discuss mainly alpha amino acids only, right? So write down here, proteins are made up of are made up of alpha amino acid. And when I say alpha amino acid, it means the NH2 group present at what? Alpha position. Huh? Right? Now you see the general structure of protein. General structure of protein. In NCERT, there are around 20 structures of proteins are given. Those structure you must go through. I will also discuss some structure now. Okay, but you must go through those structures. Now the general structure of amino acid is what? We have one chiral carbon with one group attached over here, G. General structure I am writing down. And then one acidic group we have, one amino group with this hydrogen present here. Hydrogen present here, right? So this is all these naturally occurring amino acids are generally alpha amino acids. So this is also alpha amino acid. You see this alpha position NH2 group is attached. Clear? Now the name of this compound, if this G you substitute as hydrogen, right? Then the name of the compound will be what? It is glycine. It is given in NCERT also. You must go through. If G is CH3, alanine. The name is alanine. So these names you have to memorize. You never know what they'll ask. If G is this group, CH2 with one phenyl group attached with it, then this is phenyl alanine. One hydrogen is replaced by what? Phenyl group. So it is phenyl alanine. Correct? We'll discuss some more structures, but before that, you see, all these amino acids are optically active except this glycine. That's why this glycine is one important example we have. You see, this glycine, when you substitute hydrogen instead of that G over there, right? So this carbon is not chiral anymore when you substitute hydrogen here. Fine? Yes. So if this carbon is not chiral, so there is obviously a plane of symmetry we have. So the compound will be what? Optically inactive. Yes. So in NCERT, those examples are given. Out of those examples, only glycine is only optically inactive. So you must keep this in mind. Fine. When CH3 you substitute here, then this carbon will be what? Chiral carbon. There is no plane of symmetry. Compound will be optically active. Right. Now, the classification of amino acid you see, I'll go to the next one. All of you have written this? Okay. Classification you see of amino acid. Amino acid are classified into three categories. One is acidic, other one is basic, and the last one is neutral. Okay. See, this acidic and basic nature we define according to the number of acidic and basic group present. If number of acidic group is more, then it is said to be acidic amino acid. Correct? So in this acidic amino acid, number of acidic group is more. Acidic group means what? COOH. More means more than the basic group. Group is more than the basic group. Basic group is what? NH2. So for example, you see CCOOH. Here we have CH2COOH. Here you write down NH2. and then one hydrogen. The name of this compound is aspartic acid. Aspartic acid. You see, there are two COOH group, one NH2. Right. Again, you see another structure. Carbon, if it is attached with CH2, CH2, COOH here, and then all other things are same, COOH, NH2, and H here. This structure is glutamic acid. Again, you see two COOH group and one NH2 group. Number of basic group is what? Number of NH3. So in this basic thing is what? Number of basic group is more than acidic group. Example, you see CCOOH NH2. This is the general formula we have, H here. And when you substitute this CH2 4CO NH2, CH2 4 NH2, this compound is lysine, Lysine, lysine. Okay, so this is what? This is the basic amino acid we have. Neutral one is what? Neutral one when we have equal number of acidic and basic group. Basic group. See, one thing you must be very clear. We have done this classification on the basis of number. I'm not telling you that this compound is neutral in nature or acidic in nature or basic in nature, right? However, it is true when you say for acidic and basic thing. But for neutral, if the number of COOH and NH2 group are equal, then also it is not necessary that the molecule will be neutral in nature. Okay, and that is how we get the concept of deuterion. We'll discuss that. Okay, some more structure you see. If I write down this, some more structure you just write down. I'm just giving you some general example. Okay, so carbon COOH H NH2, and when you write here CH2OH instead of G, this compound is serine, SERINE, serine. When you write down SH here, another one you write down, instead of this OH you write down SH, that compound is cysteine, CCOOH NH2 H, and here we have CH2SH. This is CYSTINE, cysteine. Another structure is this, which has the different pattern actually from the other one. CH2 CH2. Then we have CH2 NCH2 H. This is proline. Different structure it has. So you must remember. It actually does not follow the general formula we have. One note you write down into this. Each of these amino acids can exist in two stereoisomeric form. That is D and L, capital D, capital L. However, all naturally occurring amino acids. However, all naturally occurring amino acids belong to L configuration. Okay. Even protein also consists L amino acid only. Okay. Yes. Apart from all these, you just go through the structures given in NCRT. Few common structure I have done, but there are some different also maybe in NCRT. Just you go through. Okay. Now next you see is deuterion. This is important for JE point of view. See, the general formula we have here, which is for amino acid, is this only COOH G NH2. See, today we'll finish this. I'll take. There are few things left, so I think I have to. I will finish this by 7:30 only. So I will not give you any other question from any other. We'll not do the revision part today. Okay. Next class we'll do complete revision. Did you solve those ionic questions? Solving, right? Last day I gave you a chemical equilibrium question also. Okay, so that also you solve. Okay. So when you have this amino acid, you put into water, H2O. Then what happens? That this compound in water exists into this form, which is nothing but because this acid group that you have, COOH, that will lose its H plus ion, CO minus H and plus H plus. Right? Now, since this is the basic nature we have, it has tendency to accept what? H plus. Right? So there are possibilities that this H plus will taken up by NH2 and it forms NH3 plus H will be as it is. Now you see this ion is neutral in nature, yes or no? Neutral and dipolar also. Two charge point we have, so dipolar and neutral in nature. This ion is nothing but deuterion. So deuterion is what? It is a neutral ion, right? It is a neutral basically molecule, dipolar in nature. Okay, so structure of amino acid, whether it exists in uh, anionic nature or cationic nature, or anionic form or cationic form, it depends on the nature of the solution in which it is kept, or the pH of the solution in which it is kept. Right. So first, the meaning of this is what? First of all, you write on this point: structure of amino acid depends upon the structure of the amino acid depends upon the nature of solution. In bracket, you write down acidic or basic. The nature of the solution in which it is kept, and pH of the solution also. Nature or pH, both are related only. Right. Now, what happens, you see, if this ion, that is deuterion, is kept into basic solution. So basic solution means what? We'll have OH minus concentration there, and pH will be what? High. Correct? Basic solution will have high pH comparatively. So now this OH minus will take this H plus ion, correct? And forms H2O. And the molecule we get here is H2NCCOO minus. G will be as it is and H here. Now you see this neutral nature is not now possible in the solution. Correct? And this is not a deuterion because deuterion is always neutral. OH minus takes this H plus and will have negative charge over here. This we call it as anionic form of deuterion because we have one negative charge into this. Fine. Now when you put this into acidic solution means what? We have H plus concentration, pH will be less, low. So that H plus will attach over here and will get what? H3N plus C, that group COOH, and here we have hydrogen. This we call it as what? Cationic form. Right? So depending on the nature of the solution in which this deuterion is kept, it may exist into its cationic form or anionic form. Clear? Now on the basis of this, there is a concept of isoelectric point. So next heading you put on isoelectric point. Write down into this. Write down. Write down when we connect the electrode. I'll just draw a diagram. First, you write down. When we connect the electrode with an external voltage source, then the cationic ion move towards the negative rod. Cationic ion move towards the negative rod and anionic ion moves towards the positive rod. Next line. But at certain value of pH, when the amino acid exist in amino acid exist in deuterion, exist in the form of deuterion, then there is no movement towards any electrode. Right? Then what did you write? Last line. Does not move towards any electrode. This point is known as isoelectric point. Right? Now the point is what? Suppose we have a solution in this container, right? And this solution will have certain pH value, and we have two electrodes into it. right? And we have solution here. In this solution, suppose you keep amino acid into it, right? Now, depending on the nature of the solution or pH value, this amino acid, either amino acid exists in cationic form or neutral or anionic form, correct? Depending on the pH of the solution. If it is in positive form, this is connected towards, suppose, the positive plate, and this is connected towards the negative plate. So when you apply electricity towards it, then depending on the pH of the solution, if it exists in positive form, cationic form, then it starts moving towards what? Negative plate. And if it is in the anionic form, then it starts moving towards the positive plate. And we'll have some pH value here where it exists in neutral form, and neutral form is nothing but what? Deuteron. So when it exists in the form of deuteron, then there will be no movement towards any plate or electrode, correct? So that pH value is known as the isoelectric point. Clear? Okay. And these values, isoelectric point, we don't have to calculate. Okay, that is not required. Now suppose if I take some example, if I write down CCOOH NH2 CH2 CH2 COOH. What is the name of this compound? This is glutamic acid. Acidic groups are more. Isoelectric point for this compound is found to be 3.22. Right? Acidic in nature. Okay. If you write down for lysine structure I have already given you. There we have CH2 whole 4 NH2 here. Right? CH2 whole 4 NH2 here. For lysine, isoelectric point is, it is basic in nature. This one is acidic in nature. Isoelectric point for lysine is 9.87, which is actually true. Acidic, so pH value should be less than 7, should be greater than 7 here, right? But in case of alanine, alanine is what? Acidic or basic? Alanine, you tell me the structure of alanine. CH3, G is CH3. So we have one NH2 and one COOH. Ramcharan, are you there? Ramcharan Kondanya? Okay. So when we have alanine present over there, so we have one NH2 and one COH group. So it should be actually what? Neutral. So its isoelectric point should be what? 7. But this isoelectric point for alanine is found to be, it is slightly acidic, 6.02. Because COH is comparatively stronger acid than NH2. Not acid, means the basic nature of NH2 is less than the acidic nature of COH. Means what? It has tendency to lose H plus, correct? And if this NH2 has equal tendency of the acceptance of H plus, then only it will be neutral. Understood my point? COH will lose H plus very frequently, but with the same frequency, NH2 cannot accept that H plus because it is not that much basic. That's why the solution will be little bit acidic. But why we are calling it as neutral? That classification we have done according to the number of what? Number of acidic and basic group. It has nothing to do with the acidic and basic nature of the compound. However, in case of acidic and basic uh, amino acid, this is found to be correct. Right? See, lysine, it is basic 9.87, acidic, it is 3.22. But for neutral also, it will be slightly acidic only. So write down one point here. Because of a strong acidic group, neutral amino acid will not have pH value 7. Okay, so this is the discussion about amino acids. Okay, now we'll see the two different amino acid we have, which is essential and non-essential. Okay, just definition we have to go through. Just to write down next, essential and non-essential amino acid. Write down, essential amino acid are those acid which cannot be prepared by body. Okay, see, there are few amino acid which is prepared by within the body itself. Okay, inside the body actually. When those amino acid which can be prepared by the body itself within the body, that we call it as non-essential. So essential you write down first, it cannot be prepared by body. Example, you write down lysine, phenyl alanine, ALANINE, phenyl alanine, non-essential, prepared by the body itself, by the body itself. Example, you write down glycine. What is G in glycine? Then alanine. What is G in glycine? What? Hydrogen. Yes. Next, write down formation of protein or protein formation. Okay. Write down into this. It is formed by the joining It is formed by joining the carboxyl group. It is formed by joining the carboxyl group of one amino acid to the alpha amino group to the alpha amino group of another amino acid to the alpha amino group of another amino acid. Okay, now you see here, suppose the one amino acid we have, which is this H2N C. Here we have some group, suppose G1, and here we have carboxylic acid, C double bond OOH, hydrogen. This, when joins with the another amino acid NH2, CG2, C double bond OOH, hydrogen. Right. So in this, what happens when these two combines? Okay, again condensation takes place. So hydrogen here and this OH combines, H2O comes out. H2O comes out, and the product we get here is this H2NCG1, H C double bond O, NH, Cg2, C double bond O, OH, H, right? This is the product we get. Now this bond, C double bond O and N, this bond is the peptide bond. It is peptide bond. Or we also call it as peptide linkage. Okay. When there are two peptide bonds, now suppose we have another molecule here, right? NH2, Cg3, C double bond OH. So here also OH and H comes out, and we'll have another peptide linkage here, right? Then we have another peptide linkage here. Like this, we'll have a large linear molecule we'll get. Means the bonding will be linear. Understood? This is what? This is one amino acid, and this is the another amino acid. This part is the another amino acid. Similarly, we can have A3, A4, A5, A100 like this. We can have a large chain, right? With this peptide linkage or peptide bond, right? So when we have more than or equal to two peptide bond present, then we call it as polypeptide. Okay, and specifically if you write if you have two peptide bond, then we call it as dipeptide. Three peptide bond, then tripeptide. Four tetrapeptide, pentapeptide, like this. But all these comes under what? Polypeptide linkage, right? So protein forms by this polypeptide linkage only. Okay, now this peptides, you see, it has one classification also that I'll write down in the next slide. You just keep this in mind. Like this, we have n number of amino acid linked by the peptide bond, right? We have a long chain. Understood this? Okay. Now I'll come back to this again, but first you see this classification of peptides. Classification of peptides. The first one we have is oligopeptides. And the second one we have polypeptides. Polypeptides. And the last one we have proteins. This classification is depending on the number of amino acid present. This classification depends upon number of amino acid present. And so in oligopeptides, we have maximum 9 amino acid possible, 2 to 9 amino acids, right? Polypeptides, we have from 10 to 100 amino acids. Right? 10 to 100 amino acids are present, then it is polypeptides. If we have protein, then more than 100 amino acids should be present. So proteins are very complex compound, branched and complex compound. The bonding is so complex over there. Okay. Now, like I said in the structure of protein that we were discussing previously, structure of protein, you will get a long chain compound here by peptide linkage, through peptide linkage, and that will be like this: H2N CG1 H, C double bond O, NH, Cg2, C double bond O, NH, Cg3, Cg3, C double bond O, H, and like this it goes. So like this we'll get a long chain compound. Fine. So this first thing here, this is what? This is first amino acid, A1. This is what? A2. This is A3. This is A3, right? And all these amino acids are bonded together by what? What is this? By peptide linkage, right? Peptide bond or peptide linkage. Okay. Now, actually, what happens since we're talking about proteins, right? We're talking about proteins. So we have more than 100 amino acid present like this. And since it is a long chain where we have 100 amino acid, so it cannot be completely straight, right? Since it is a long chain, if long rope also if you take, it is very difficult to keep that rope straight, right? But here it is what? You see this oxygen carbon, some group we have here, nitrogen. So obviously we have some electronegativity difference also here, right? So first point is what? The structure of protein is can be explained in 4 different stages, right? This long chain compound, when you have only a linear chain, there is no branch into it, right? A1, A2, A3, A4, A5, A100, 110, 200 like that. This linear chain that you have, we call it as primary structure of protein. Correct? When there is no branch, primary structure. Now, since it is a long chain, so it won't be completely straight. Secondly, there is some electronegativity difference also here. So we'll have some attraction in these molecules, these atoms present over here, right? So because of this attraction, what happens? This structure will be bent in the form, in spiral form or helical form that you have, spring-like structure you get. So that structure, let me draw. Like I said, that it won't be like the structure of the primary structure won't be in the straight chain, but it will be in the form of a spring, right? And that structure will be like this. It's not that good, but it will be bent at some point because of the attraction due to the electronegativity difference also. Understood? Here we have, if you see there, we have NCC, then again NCCN, then again CCN, CCN, like this we have. You see the previous one? We have NCC, 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 like this it is going. You see the previous structure, A1, A2, A3 that I have written. Okay. NCC like this we have. So due to some electronegativity difference, some molecules, some atoms will be close enough. There will be an interaction between them, and then they won't be available, or there won't be a straight chain compound, but there will be some an attraction. Because of that attraction, it exists in helical structure or spring-like structure. Okay, and this we also call it as alpha helix. Okay, I am not giving you the theory part into this. I'm just explaining you. It is written in NCERT very clearly. So today only you go through. Okay, so when you talk about this helical structure, this comes under the secondary structure of protein, right? Primary one what? The straight chain, and it is the secondary structure. Clear? Right. Now, since again this secondary structure we have helix is also very long, right? It's not small. It's very long chain, more than 100. 100. We are just taking a reference, but it will be in lakhs or thousands of amino acid present in protein, right? So because of this, you see this structure will not be also very straight. It is also bent at some point of time. So that structure you see that the tertiary structure that we say is something like this. This helical structure will be like this, but at some point it will be bent like this. Like this it is there. Some random structure will be there like this. So this structure we call it as bent structure. Again, you see, we'll have some electronegativity difference here also. So there will have some interaction. Suppose this point and this point, some interaction we have. So this will be bent like this. Okay. And anything, it is a very long chain. So again, it is very difficult to be straight, completely straight. So it will be bent at some point of time, some point like this, randomly, right? So this bent structure, when you explain this bent structure, it comes under tertiary structure. Tertiary structure. It comes under tertiary structure, right? Various kind of bonds are involved into this. Forces are involved into this. That can be intramolecular hydrogen bonding. Okay, salt ionic is interaction, maybe van der Waals interaction, maybe. That is, there are many structures possible. Many kind of intermolecular attraction possible here, right? So completely straight one is primary, helical is secondary, and this bent structure is tertiary, right? Now, this kind of bent structure you see, first of all, we have, I'll just draw this here. Suppose this is the bent structure we have, and this gives you one protein like this. Okay, sorry, one protein like this. So in this you see, this is a one protein we have like this. Again, because of electronegative difference, we'll have some charge separation onto this point, that carbon, oxygen, and nitrogen that we have here. So we have, suppose this is P1, first type of protein. Like this, we have another structure also, another bent structure also. So those negative part of that bent structure will attach with positive part of this and vice versa also. So this is surrounded by the another bent structure of another protein like this, or another bent structure of another protein like this, or another bent structure of another protein like this. Like this, we can have any random structure possible, right? So this structure, I know it is not that good, okay, but it is random only, right? Like this, anything I can draw. So it is a random structure. So you see, this is P1, this is suppose P2, this is suppose P3, this is P4. Like this, one protein structure is surrounded by many other different proteins, right? Because of some electronegative difference, some positive negative charge center we'll have here, and then we'll have some interaction. So this structure we explain under quaternary structure of protein. Quaternary structure of protein. Right. So this is nothing but the protein. The actual protein is this quadrant is a very large, complex, random structure we have. That is protein. Right. So I've given you the brief discussion of this. Okay. In NCRT, you don't forget to read it today itself. Okay. In NCRT, you see there is a structure of protein is given: primary, secondary, tertiary, and quaternary. So if you go through it, you will understand how this protein forms. Okay, but again, for JE point of view, not important. Board also, I haven't seen there was a structure of protein, but yes, just go through once. You can write down in your own words. Okay. See, the body temperature generally it is 37 degrees Celsius, right? Human body temperature is 37 degrees Celsius. When what happens when the temperature changes? If suppose 37 to 39 in case of fever, the body temperature increases, right? And when temperature increases, the structure of protein changes because, and that is why we'll have some problem then, right? Structure of protein changes, and then we'll get some problem, and for that, to cure that, we need some medicine. Okay, so when the temperature increases, the structure of protein also changes. Okay, this we call it as denaturation of protein. Okay, with temperature, when the structure changes, a structure of protein changes, we call it as denaturation of protein. So this term you must keep in mind, denaturation of protein, right? So this is it in this chapter. Lipids and all, that is not important. Okay, don't need to uh, study all those. Okay, so for today, you just go through the at least the structure of proteins and the various amino acid given in NCRT. That is more than enough. Okay, one note you write down here. One note you write down. Insulin contains disulfide bond. Insulin contains disulfide bond consists of two polypeptide chain. Only thing you have to keep in mind, because once in NEET exam they have asked that which of these molecule contains disulfide bond. So insulin contains disulfide bond. That is only one thing you must remember. Okay. Okay. So this is it for this chapter. We are done with it. Okay. You revise those through NCRT, just go through, and previous year question you see. Don't put much time into this chapter. It is not that much important. Okay. Try to go through the previous year questions, and then those things you must keep in mind. Okay, because there are many theory into this. Anyway, so one last thing we'll discuss. Kondane asked me one question, that how to convert benzoic acid into benzaldehyde, right? Okay, just a second. I'll show you one thing. See this one. Can you see this? See, benzoic acid to benzaldehyde conversion. If you use this LiAlH4, you'll get CH2OH. Then PCC converts into this. Your question was, we have to convert benzoic acid into benzaldehyde without converting. Huh? Directly is not possible, because if you remember, I have discussed this, that this carbonyl group you have to preserve. When you directly use some reducing agent here, it will convert into benzene directly, because this CO carbonyl group is not preserved. To preserve this, first of all, you can convert this into chloride also, like you see this example, PCl5. You can also use SOCl2 here. I have done this, you just go through your notes. When you convert this into chloride, then this CO is preserved now. After that, you can use this Rosenman reaction, PDBaSO4, right? Then you'll get aldehyde here. If you ask me direct conversion, not possible. If you use reducing agent here, this will gives you benzene, right? So that we cannot do. First of all, we have to preserve this carbonyl carbon, and for that we can convert this into chloride with the use of that SOCl2, PCl5 and all. We can convert this to COCl, and then we can reduce this with Rosenman reaction. Then you'll get benzaldehyde into this. Understood this? Okay, so you have to form that intermediate chloride compound SOCl2 with SOCl2 and PCl5. Fine. Anything else? What are you revising nowadays? Hmm? Inorganic. How do you revising your? How are you revising inorganic? So one in one day, how what one chapter do you finish? Fine, that's fine. NCRT you're doing, right? You just go through with NCRT. For inorganic, NCRT is enough. Little bit more information if you want, you can go through some other book. But just you roam around that previous year question only. Don't look at all those theory. Okay, that is not helpful. Okay, and what about 12th portion? Do you have any doubt in the physical portion of 12th? Do you solve previous year question? All of you I'm asking. Ramcharan, Kondanya, Naman, Aditya. Where is Aditya? So 12th portion physical chemistry 12th portion. Do you have any doubt or you have solved previous year question? Okay. Organic you are doing? Okay, fine. So next class I'll do some concepts of GOC, okay, general organic chemistry I'll discuss with some questions. Basically we will see mainly questions into that, how to compare the stability of RS and various other compounds, right? So there are 7 8 rules we have for comparison of acidity basicity comparison we'll see. Okay. So GOC little bit concept we'll discuss. Okay. 11th portion, do you need any chapter revision for 11th portion? What? Okay. See, do one thing, mole concept, okay, mole concept and mole concept 2, which contains the question related to equivalent normality and all, equivalent mass, number of equivalents, okay, and the electrochemistry chapter that you have, there we have questions on Faraday's law. So that Faraday's law also involves the concept of equivalence, equivalent mass and all, if you remember. Q is equals to M is equals to ZIT will write, okay. Z is electrochemical equivalent, all those. Okay. So when you solve those Faraday's law, so that will have required the concept of equivalent mass and mole concept also. So once you do this mole concept or equivalent mass question, you try to finish that portion also of electrochemistry, Faraday's law of electrolysis. Okay. So generally in JE they ask questions, they mix the concept of 1 or 2 chapters. Like in ionic equilibrium, you see solubility product. And then in electrochemistry also we have some question related to electrode potential solubility product and all. I have done few questions in the class also. Okay, so when you solve this solubility product, you also do that electrochemistry problem also into that. Okay, chemical equilibrium is not that tough. Okay, only some basic concepts and Le-Chatelier principle application you just go through. Okay, states of matter A and B, compressibility factor. Okay, those things are important. Some graphical relation, velocity relation, that various molecular velocity, VRMS, V average, and all graph related thing. Those you go through, and then we are left with thermodynamics. Thermodynamics, thermochemistry is important again. Okay, we have done this enthalpy of formation and all. In ionic, in this chemical. Acha, acha, ठीक है. So next class we'll do that also. Okay. GOC concept and we'll do discussion of GOC. Gives free energy also. What? Yeah, no problem. Like GOC, will you do? We'll discuss questions only. not in the form of question. Like I'll give you few compounds, and what is the stability, what is the acidic order of that. Like that we'll discuss. And in physical, we can discuss questions and then concepts related to the questions. No problem with that. Okay, Naman, what happened? Did you send? What happened? This? Huh. Just a second. What is the doubt in this? H2O H3PO4 gives this. pK1 pK2 is given. pH of this. Okay. This is a question of polyprotic acid. Okay, I'll discuss this concept. Okay, Naman. Because last class I haven't done with this because generally we don't get this kind of question in the exam. But actually, you see, in this what happens? This H3PO4 in the first reaction. Okay, you don't have all this question, no? Anyways, let it be. I'll discuss this question next class. Okay, I'll give you the concept of how to do the polyprotic acid. This is actually the simultaneous equilibrium you have to use into this. Okay. Uh, okay, let be. I'll discuss this next class. Okay, I'll tell you. Okay, ठीक है चलो. Next class we'll start GOC and some concepts of ionic, and that we'll see. Okay. Okay. Thank you. Thank you.